her alanındayım.
Dear attendants, Modeling, Simulations and Integrated Design is the title of our technical session number 5. In this session, we will have 4 speakers. We start now with the presentation of Professor Birol Kılkış. The title of his presentation is 4 Exergy-Optimum Prongs of Carbon Footprint in Geothermal District Heating. Dear Professor, please introduce yourself a bit, and the floor is now yours. Please.
Thank you. I would like to extend my great appreciation to the entire organization committee and TTMD for letting me to speak to the audience in this very important organization by TTMD, which is the 16th TTMD International Conference, and this is very important. And it is my honor and privilege to be here today.
Thank you.
My speech, before my speech, I would like to tell about a few words about myself. I am a graduate of Middle East Technical University and the von Karman Institute in Brussels. And I am a fellow HVAC, distinguished lecturer, and I have other distinctions from HVAC. And currently I am a full professor at Austin Technical University. And I have just stepped down from TC7 for HVAC Technical Committee on Exergy. And my talk will be related to the Exergy. So I can start with, I think. And let me try to share my screen first. My presentation title is about 4 Exergy-Optimum Prongs of Carbon Footprint in Geothermal District Heating Systems. In other words, I would like to explain what are the major parameters in optimization of decarbonization of geothermal district heating systems. The 4 prongs are given in this slide. The first one is the geothermal well itself. We get provided there is enough enthalpy in the geothermal well fluid, we can get power, electricity, and heat at the same time. The heat may be distributed to a district distance circuit to feed the district for heating, and probably local cooling using absorption or adsorption cooling systems if the temperature is high enough. And they say that the amount of heat that we can distribute is Q. And in the district, we distribute the heat for prosumer buildings or just regular buildings by prosumers. And the well depth is a function because deeper the well, higher the temperature we get. But deep well means large embodiments of carbon dioxide, energy, and also cost. And the supply and the injection temperature are almost fixed because the injection temperature may not be lower than about 40 degrees Celsius. And of course, you have reference temperature in the environment. The district distance is also limited by L, the distance in kilometers, because the amount of heat that you can deliver to district Q is known from the geothermal well, which is the prong 1. The prong 2 is the district circuit piping. And in this case, it cannot be too farther away because the pumping exergy, the electricity that you use for pumping, may exceed the exergy supply from the geothermal well to the district. So there's a limitation. And in the district, you may consider slow cities, green agriculture, biogas regeneration, electric mass transit or mobility, and sewer heat may be added on. So 4 prongs are: number 1, the well, the district distance, between the wells, the geothermal field with the city and the prosumers. They are all linked together. As I mentioned, the maximum length or the maximum distance from the geothermal field to the district is a function of Q. Q is the heat that is delivered. It's a function of Q to the power 1.5. And the supply and the return or the injection temperatures are also a factor. And C is a constant depending upon your piping, the piping internal frictions, the viscosity, etc., and the pipe material. And as you see, equation 3, C is also a function of the first law, the efficiency of the pumping engines. And the pressure head that has to be delivered by pumps must be less than the exergy of the heat delivered. 0.95 is actually the maximum exergy that can be obtained in electric generation, for example. And the supply temperature, as you see, is important to define your delivered exergy. And the injection temperature is almost fixed. The minimum temperature is about 40 degrees Celsius. So we have to pay attention to these cases a little bit. And as you see, the geothermal well may have been used for different purposes like electricity generation. By increasing the well depth, you may increase the thermal exergy that you can extract and deliver to the district and to the buildings. Is a function of the well depth, which is also going to cause large embodiments, carbon dioxide embodiments, material embodiments, energy, and cost. So there's an optimum. To define all these on a common base, we define an rational exergy model efficiency, sigma R, which is the ratio of the total demand exergy divided by the supply exergy, which is in this case the geothermal well exergy. And it can be defined by equation 7 and so forth. And we can go further. This is a simplistic diagram just to remind that deeper the well, higher the temperature, but inline pump, if there is a pump to pump this geothermal heat, the fluid to the surface, we need a pump there also, and this pump has a carbon dioxide emission responsibility because it is using electricity mostly and probably coming from a fossil fuel power plant. And also because this electricity coming from the power plant is not free from the carbon dioxide component, which we call it the carbon dioxide that can be largely eliminated. This is the responsibility because the power plants usually do not use the heat, but they just spend it to the air or to the environment like cooling towers. So a pump means a carbon dioxide and additionally carbon dioxide emission responsibility depends upon where the electricity comes from. If it's coming from PV, solar PVs, again, the solar photovoltaics do not utilize normally the heat that sun delivers to the PV panel surface. So every renewable energy has also delta CO2. So we have to consider all these. When we add all these functions, which I am not going to delve into details because they are available in my paper, the optimization is possible because deeper the temperature, the well depth, and higher the temperature, we can use organic Rankine cycles or even steam turbines, whatever, for electricity generation, which is also a desirable output from geothermal energy resources. And when we add all these down, we also get an optimization equation like 18, how much depth we should have, what is the temperature, what should be the efficiency of the organic Rankine cycle. And at the same time, we can also think about, should we dedicate the geothermal well only for electricity production or partially thermal power generation? Because thermal power generation means lower temperatures for the reinjection well. Reinjection well, if connected to the production domain, then you reduce somehow the electricity production lifetime, because you are actually cooling the reservoir to a certain extent. So Y and X are also optimizable to see how much heat should be dedicated and how much the depth should be. As you see, these are the results of the equations available in my paper. The power on the case may go up to the reinjection temperature of about 335 Kelvin. Higher than that, we should use maybe only power, but below these temperatures, power and heat is feasible because the unit exergy rendered, including both power of electricity exergy and thermal power exergy, the result at, for example, 310 degrees, 310 Kelvin, the reinjection temperature, which is about 40 degrees, you get the maximum output, which is belonging to power and heat, not power only. The power only is slightly below. It's slightly less than 0.2, but when you get the reinjection temperature lower to the lower limit, you can have unit exergy render up to 0.23 kilowatt hours per kilowatt hour of energy. And on the right hand side, as you see, we can also optimize how deep our well should be, depending upon the temperature. As you know, deeper the well, higher the temperature. Therefore, there is an optimum, and this optimum is also, by a good coincidence, is around 340 Kelvin. So it proves that the reinjection temperatures must be as low as possible down to the limit where you can get maximum power from the geothermal well at about a reinjection temperature of about 340, and by coincidence it also corresponds to, in this specific case, 360 meters, not more. A shallow well or a much deeper well may render a high temperature, but due to the embodiments, the optimum is somewhere in between, about 360 meters, not more, not less. So these are the tools to derive the maximum exergy, the useful work potential from a geothermal well, including the 4 prongs, including the distance where you can deliver the heat, has a maximum equation that I have already mentioned to you. And these are the prong 4, let's say, where you have prosumer buildings, where you have solar photovoltaic thermal on the building. You may have their own geothermal, small well, and etc. And I also show an advanced solar PVT system where it has a layer of thermoelectric generators which also produce additional electricity due to temperature difference between the phase change material and the PV material. And to increase the thermal output, we have a flat plate layer, a glass layer, and of course heavy insulation, and there's no pump, because pump means electricity demand, and part of the PV output goes to the pump. So this case is not a reasonable case, and we use heat pipes, renewable heat, adjustable heat pipes in angle, so that we trace the maximum temperature in the PCM layer, so that we get the maximum heat output without use of a pump in the main primary circuit. Of course, in the building circuit, there are pumps, but not on the PVT. It uses heat pipes. And another example that we should be careful about, let's say this is a geothermal well where you just cool the system by electrically operated fans. And these fans, of course, lose the opportunity of using the heat in district heating system, just rejecting to the air. These fans also demand large amounts of electric power, and therefore most of the power in some cases just goes to the cooling system. And on the right you see a cooling pond or something that releases carbon dioxide and cools down the geothermal fluid, which is a loss of exergy again. So these are the problems that we should consider in having the maximum and sustainable output, thermal and electric together at an optimal ratio for a geothermal well. It is actually, from equations wise, simple, but it is sometimes gets complicated to think about. And another example may be, in this case, greenhouse assisted slow city and PVT panels in a farm, including husbandry and a pond which collects extra water during storms, and combined with a solar house, solar prosumer, electrical mobility, PVTs, we can overcome the hurdles and the problems of simple geothermal energy use. Another case study, the current TOKİ buildings in Afşin Elbistan are about 3 to 4 kilometers away from the return piping of the Afşin Elbistan power plant. The power plant is cooled from Ceyhan River to a 30 kilometer of steel piping, and the coolant water returns after cooling the power plant is fed back to the original point of the Ceyhan River, which warms the river. It is not a good idea for environmental reasons, and it passes only about 4 kilometers away. And there are some geothermal reservoirs there. And as you see, we could actually heat and cool and provide the power of these TOKİ buildings simply by using the waste heat, as you see here, in a mini district heating system. And using the same principles, you can optimize it, and you could have about 85% of carbon dioxide emission reduction. And this is the diagram where you can follow in the paper. And again, by simply tapping in the waste heat from a power plant versus making the city or the buildings green has a balance. Because if you tap in the waste heat rather than losing it in the cooling towers, for example, this means that the carbon dioxide emission responsibility plus the carbon dioxide emissions of the green city are balanced. Lower carbon dioxide emission responsibility from the power plant. But at the same time, if you make the city as largely green, totally green, no energy demand, then there is no mean of using the waste heat of the power plant. So using the waste heat means you are reducing the responsibility of the power plant carbon dioxide wise. So there's an optimum. The green city should be green, but not totally green, to be able to tap in at this part of the waste heat, which otherwise could not be possible. So we define an Exergy star, which means according to the relation Exergy management model, the green Exergy application starts from 0.7, and in this Afşin Elbistan case, the optimum was about 4 Exergy stars, not 5. Because if you make it 5, yes, you reduce the carbon dioxide in the city, but you are increasing the responsibility of the power plant because you are not using the available heat. So this is another final point that I would like to bring to your attention, that green cities and green industries are going to be carefully designed, and they should share optimum levels of waste heat. These are some equations and some results that I would like to share and in my paper if it is published. And thank you so much. And this is the end of my presentation. Thank you for reading and attendance. Thank you.
Thank you, Professor Kılkış. I think those of us who are interested in assessing your findings more in depth can visit your or can read your paper on this. I think they can Google your name and find this paper somewhere. do you want
I
to
will-
add something?
I
Yes.
I have the paper with the organizing committee, and therefore
Okay.
they may distribute, and I will be, of course, available anytime for any questions.
Okay.
And as a member of TTMD, I will be more than happy to assist
Thank you.
the questions. Thank you so much.
Thank you very
And
much.
my best greetings to all of you. Thank
Thank
you.
you very much. Thank you very much. Now it's time for me to invite the second speaker of our session, number 5. The title of the presentation of Said Bolluk is an introductory overview of urban building energy models. I remember Said from the student competition of TTMD. I think he has a very interesting presentation waiting for us. So the floor is yours, Said. Please introduce yourself first, and then you can share your presentation.
Thanks so much for your good words, Ahmetcan. Hopefully you can enjoy my presentation. Hello everyone, it's good to be here. Let me share my screen. Okay. Hello again. Let me introduce myself quickly. My name is Said Bolluk. I'm a graduate teaching assistant at Özyeğin University. I also study for a doctorate in civil engineering at Özyeğin University. Today I will talk about the urban building energy modeling and its importance in sustainable urban planning. So let's start with the description of urban building energy modeling. UBEM is a modeling approach that we can assess building energy performance at the different spatial scales of urban areas. While developing UBEM, the aim is to generalize the characteristic of urban building stocks so they can be modeled collectively. And to do this, we use the archetypes, which are the representative buildings for buildings with the same building morphology and also the same, let's say, energy consumption patterns. This archetype approach reduces the level of details in building-specific modeling, while enabling the mass energy performance analysis of the urban building stocks. There are the UBEMs are basically used in understanding the factors that drive the urban building energy consumption. These models predicted the building energy performance over the urban building energy stocks at various spatial and temporal resolutions. And with these models, we can develop urban level energy reduction strategies and also the carbon emission reduction strategies for the urban building stocks. In UBEM, there are two main approaches, and these are the top-down and the bottom-up approaches. The top-down approach is utilized in more general and long-term planning that can include the economic growth and technological advancement studies. On the other hand, bottom-up models can provide more detailed analysis while requiring more detailed information about the local climate, the building characteristics, and also the occupant behavior within the observed area. And in the bottom-up approach, there are two main modeling techniques, let's say, and these are the statistical and dynamic models. So I will start with the statistical urban building energy models. So statistical models are practical to identify the building energy consumption characteristics using the historical data. These models form connection between the input and the output data without requiring any specific scientific reasoning. Therefore, they can be efficiently trained and they can provide reasonable and quick predictions only using a moderate amount of input data. However, while developing the urban building energy models, we rarely found the input data in the, let's say, sufficient amounts at the required spatial and temporal resolution. Also, the statistical models suffer from the, let's say, they struggle to incorporate time-sensitive variables. These can be the changing climate conditions, the building's operational schedules, and also the thermal interaction between buildings. And with all these statistical models require more spatial and temporal detail for further, for elaborate urban level planning strategies or analysis. On the other hand, dynamic models can analyze the buildings within multiple time zones and within different time intervals. And they can offer high-resolution simulation results as they are physics-based, these models are physics-based models, and as they can include time-dependent changes or within the building operation and also the thermal interaction among the building stock. However, these models require extensive data sets, such as the building characterization data, the geometrical data, the local weather data, and the high-resolution validation data. And this is a very challenging task at the urban scale with lots of buildings. Also, these models require large computational resources and time to perform simulations. Okay, so I want to talk about the practical utilization of UBAM in sustainable urban planning. One crucial application of UBAM is supporting to monitor and manage urban building energy consumption for the urban planners and authorities. This ability helps reduce building energy consumption through retrofitting, and this retrofitting could be either upgrading the HVAC systems or adjusting the building envelopes thermophysical features or adjusting the operational schedules. Also, UBAM can assess the potential environmental and economic returns of the photovoltaic energy production, renewable energy production. And with the help of these models, we can perform accurate energy consumption predictions, and this accurate energy prediction can help balancing the supply and demand in the urban power grids. Therefore, UBAMs are promising urban planning tools, and they can help us to develop urban level, countrywide energy reduction strategies, actually. So let us now check some example of UBAM. I will start with the the examples for statistical UBAM. And for the first example, Ma and Chang developed a statistical UBAM to analyze the annual operational energy consumption of buildings in New York. And for the second one, the Gassar analyzed the consumption of buildings within the low and medium populated areas in London. For the third one, Tuzani compared different statistical UBAMs in predicting the monthly energy consumption of more than 400 commercial buildings in the United States. And for the final statistical example, Koshwitz evaluated the climate conditions and the building operation schedules in predicting the cooling and energy consumption and predicting the cooling and heating loss of more than 200 buildings in Germany using different statistical models. And for the dynamic side, the first example is from the Chen, where they develop a physics-based models to analyze the operational energy use of almost 1,000 commercial buildings in San Francisco. For the second one, Sokol developed a dynamic UBAM and analyzed the natural gas and electricity consumption of more than 2,000 residential buildings in Cambridge. And finally, the Hedegaard developed a dynamic UBAM to evaluate the space heating consumption of more than 150 buildings. And using this model, they manage the peak hour demand from the domestic hot water consumption. So we see that both the statistical and dynamic UBAMs can have the potential to provide accurate energy consumption prediction and the potential to support urban planners to develop energy reduction strategies. So I want to talk about the several common dynamic modeling tools in urban building energy modeling. These models are either available for open access or not. For example, the urban modeling interface, teaser, and city energy analysis are open for public access, while the city-based is not. And I want to talk a bit about the urban modeling interface from the MIT Sustainable Design Lab, since UMI is a highly regarded modeling tool to develop energy and carbon reduction strategies through retrofitting and integrating photovoltaic systems. So therefore, we focused on the utilization of UMI with few examples. So let's check them. By modeling the urban districts around the world, academicians and urban planners achieve some significant amount of carbon dioxide emissions, estimated some significant amount of decrease in the carbon dioxide emissions utilizing UMI. For example, a 60% reduction in carbon dioxide emissions in Dublin, 81% reduction in Brazil, in Florianopolis, 36% reduction in Singapore, 89% reduction in Montreal, and finally 40% reduction in Braga. These are the current utilization of UBAM in practice. We also utilize UBAM in our studies. We have two ongoing projects that we use UMI. The first one is a university campus in Çekmeköy, as you can see on the left-hand side. And the second one is a residential area in Ataşehir, as you can see on the right-hand side. After this practical utilization of UMI, I want to talk a little bit about the future of urban building energy modeling. So either from the statistical predictions or the simulation results from dynamic models, the literature shows us that the output of the urban building energy models are very essential to analyze the energy consumption at district and hourly resolution and identify peak hour demands in the urban power grids. Also, we can assess the impact of building components and weather conditions on the building energy use using urban building energy models to drive different energy reduction strategies. For example, I just said the retrofitting strategies. And finally, as I told you, we can drive energy efficient design strategies for our urban building stocks. However, there's a main challenge when working with UBAM, and this is obtaining hourly measured energy consumption data for urban building stocks, because this is a very rare data set with for building specific validation data. So to solve this problem and also further increase the utilization of UBAM, researchers are working on some future directions, and I will summarize them for you. So I have three main research directions that I summarize for you. The first one is generating synthetic hourly energy consumption data using the available validation data to compensate for the missing validation data at the high temporal resolution, for example, the hourly resolution validation data. The next option could be working with advanced deep learning models to handle with the noise in the input and validation data and eventually increase the time series prediction of the building energy consumption. And finally, combining the strengths of statistical and dynamic models can provide accurate energy consumption predictions while being reasonable with the required input data and the computational power. So this is it. This is my presentation. Thank you for your time, and I can have your questions right now. Also, if you want to further discuss about UBAM, you can contact me by my email and LinkedIn pages. Thank you so much.
Thank you very much, Said. I think UBAM is a very handy tool for future decision makers, engineers, architects, and I'm sure there are people among us who would like to get more information from you in that respect. With this, I would like to pass to our third speaker, Mr. Yetiş, Ahmetcan Yetiş. The title of his presentation is Utilization of Full Factorial Experimental Design in Indoor Thermal Comfort Estimation in a Classroom. So the floor is yours, Mr. Yetiş. We can't hear you.
I will be giving some. I will begin with a brief information about the impact of thermal conditions on children and quantifying thermal comfort. Then I will continue to introduce our classroom model, which we were investigated. And next, I will provide some data about ventilation requirements that we were investigated, thermal comfort parameters, and some list of factors that are involved in this study. Before giving you the results, a mesh and time independency analysis will be also shown. Students spend nearly 16,000 hours by the time they graduate from high school. Especially younger children are more vulnerable to environmental quality due to having higher metabolic and respiratory rates when compared to adults. They have limited cognitive capacities, and because of that, changing the environment according to their needs is difficult for them. Thus, predicting their needs and responses to thermal conditions is crucial to improve children's health and academic performances. Which brings us to predicted mean vote and predicted percentage of dissatisfied parameters. PMV is a 7-point thermal sensation scale to investigate the mean value of a set of occupants' votes. And PD attempts to investigate these votes and estimate the percentage of people likely to feel uncomfortable. The recommended limit on PMV scale, according to HVAC standard 55, is between minus and plus 0.5, and the corresponding PPD is 10%. Here are some parameters that we used in PMV and PPD values calculation. These parameters include metabolic rate, floating insulation, air and radiant temperature, relative humidity, and air velocity. The formulation also includes floating surface temperature, convective transfer coefficient, floating surface area factor, and mechanical power, which some of them are related to previously mentioned parameters. A classroom located in Izmir, Turkey has been modeled with a concept ventilation scenario for this study. A simple sketch of the classroom can be seen on the figure on the right side. After the creation of model, ventilation requirements are determined according to investigating some related standards. Then our boundary conditions are defined for CFD analysis. Before continuing with the simulations, a mesh and time dependency investigation also have been conducted. The ventilation of the classroom in the model have been provided by 4 monoheat recovery units. These units have angled inlet and outlets to prevent short circuit of fresh air. As can be visualized on the figure below, diffusers facing each other are intended to perform same function to cross fresh air streams to effectively reduce air velocity at inlets. In these simulations at higher flow rates, inlet air velocities can be as high as 1.78 meters per second. Therefore, reducing air velocity to more comfortable levels is a must. In separate analysis, air inlets were directed towards ground with 0, 5, and 10 degrees to investigate the effect of angling. To determine the ventilation rate for the classroom, we have looked into American, British, and French ventilation standards. Different ventilation rates are determined for each standard. To simplify, 400, 600, and 800 cubic meter per hour ventilation rates are determined for the total ventilation rate of the classroom. In numerical analysis, mean values of air velocities around students' heads were calculated locally. Metabolic rate and clothing insulation of students were accepted as 1.1 and 0.8 respectively. Air temperature and radiant temperatures were assumed equal, and 3 different temperatures were investigated, which are 22, 24, and 26 degrees. Mean relative humidity value of Izmir, Turkey in July was selected, which is 51%. With the obtained PMV values, the full factorial design method was used in analysis of the investigated factors, as can be seen in the figure below. Analysis of variance tests were made to investigate statistical significance of each factor that are listed here. PMV response values are calculated according to 3 different flow rates, angles, and temperatures. Response values of the students were then examined with 95% confidence level. All simulations in this study are conducted with ANSYS Fluent. The air was assumed to be incompressible and its physical properties are assumed constant. No penetration and non-slip conditions are imposed at all wall boundaries. The supply air inlets are defined with magnitude and direction, so orientations of airflow can be defined with respective Cartesian vectors to effectively simulate angling of diffusers. Outlets are defined as pressure outlet boundaries with a minus 50 Pascal negative pressure in all investigated scenarios. And all scenarios are conducted with isothermal conditions. Pressure-based steady-state fluent solver have been used in all investigated scenarios, and realizable chi-epsilon model was utilized to characterize flow field inside the classroom. 3 meshes with different parameters were created for the model to investigate mesh independency. Sizing of these meshes are given on the right bottom side, and statistics of the created meshes are given in the table on the left side. To identify these meshes, we decided to use first 2 numbers to define the element size around the head, and the last 2 numbers define the size of the mesh in the whole volume of the classroom. In general, low skewness, high element and orthogonal quality are wanted in these meshes. Statistics of these created mesh structures revealed us that the quality of these 3 models are very similar. To investigate in detail, we decided to conduct some CFD analysis with a ventilation rate of 800 cubic meter per hour with an angling of 10 degrees to determine the mean air velocities around student sets. These obtained values were then compared with root mean square and normalized root mean square error methods. When the results of analysis made with these 3 meshes are compared, it was deemed appropriate to use a C2075 model due to having relatively low error when compared with these other more dense structures. Then, before giving the results, I will give some information about the fluent solver type. We conducted transient and steady state analysis with this C2075 model. 2 transient analyses with 0.5 and 1 second time steps were also conducted to investigate time step independence. As can be seen on the table and in the figure, time step sizes have very small differences, which is a root mean square error is 0.00032 and normalized root mean square error at 0.3%. So because of that, we decided to continue with 1 second, and when we investigated steady state and transient states errors, we see an NRMSE or a root mean square error of 0.012 and NRMSE or normalized root mean square error with 12.3%. Considering time management and compatibility issues, it was decided to perform these analyses with steady state conditions. While air velocity is reduced rapidly before reaching the breathing zone, uneven air distribution was observed throughout the whole classroom when these analyses are conducted, especially when angling the diffusers are involved. In the 3rd and 4th rows of the students, velocity fluctuations are highest. While mean PMV value of all students at 22 and 24 degrees is within the recommended range of HVAC standard 55, 26 degrees were perceived as slightly warm. When these mean PMV values are examined in 3x3 full factorial experimental design method, all factors were seemed significant at a 95% confidence level. As mentioned previously, uneven airflow inside inside the classroom, resulting in different experiences between students. Because of that, in the next part, we have investigated each student separately to effectively understand which parameters is significant or not for a student inside the classroom. Same ANOVA tests were also performed on locations where uneven airflow distribution experienced most, as these students are shown in the figure on the right side. Students that have been selected are numbered to increase comprehensibility. Here we can see the PMV values of all selected students. Compared to previous table, which also shown in the figure as a small reminder, some interesting differences can be seen. Even though mean PMV value of all students is within recommended levels, in simulations with 22 degrees, especially at higher flow rates and diffuser angles, some of the selected students' thermal perception is calculated as slightly cool. Students are affected by flow rate, diffuser angle, and temperature factors to different degrees. So a detailed investigation is important to determine the effectiveness of the ventilation system. With the PMV responses obtained from selected student group, ANOVA tests were conducted separately this time, while for students 2.1, 2, and 3.1, flow rate is seen as non-significant. And for student 2.6, both flow rate and angle is not significant parameters for providing thermal comfort. For the rest of the selected group, all parameters are significant and temperature has appeared as a significant factor in all scenarios. So to conclude, a real-time classroom have been modeled with a concept decentralized ventilation scenario with 4 equally sized mono heat recovery units. Air velocity around students' heads were calculated through numerical analysis according to different flow rates and inlet diffuser angles. With these obtained velocities, classrooms' general and local PMV values were obtained. PMV responses then investigated by an experimental design method to investigate significance of each parameter. As a result, flow rate, temperature, and angle are seen as significant in providing thermal comfort all around the classroom. However, air distribution is not equal, thus it is needed to investigate each student separately. A group of students were selected and same ANOVA tests were performed. In the end, it was observed that the significance of each parameter varied at different locations. In the end, statistical methods are effective tools in assessing performance of ventilation systems, and investigating environment locally instead of as a whole is important to determine the effectiveness of the ventilation system and ventilation equity. Thank you for listening, and I'm open for your questions from now on.
Thank you very much, Ahmetcan. I assume you have not conducted an experimental analysis later on because the system is not implemented in the classroom, right? It's
yes, unfortunately.
Unfortunately, yeah.
Mm-hmm.
But do you plan to do such an investigation in the future? Would it be possible if you agree with the school?
If an opportunity arises, we also wanted to investigate the detail and with experimental analysis. Yes.
Okay. That's very good work. Thank you very much.
Thank you, Murat Bey,
for your presentation. And this brings us to the last presentation of today, which will be presented by Alper Mete Genç. The title of the presentation is Experimental Investigation of the Characteristics of Triply Periodic Minimal Surface Heat Exchangers. We are a bit ahead of time, but Alper Mete Genç will have minimum 20 minutes of presentation time. So with this, I invite you to take the floor, Mr. Genç.
Okay. Thank you, Mr. Çakan. Can you hear me clearly?
Yes.
Okay, nice. Hello, I am Alper. I have finished my PhD last August. Also, I am working at Bosch company as a hydraulic design engineer. So I will present to you experimental investigation of the characteristic of triply periodic minimal surface heat exchangers. In the contest, I will start with the introduction part. I will present the decentralized heat recovery ventilation units, mono units, triply periodic minimal surfaces, and additive manufacturing. In the second chapter, main parameters, building TPMS geometry, and the experimental setup. At the third chapter, I will explain the result and discussion. And the last chapter, conclusion part, general conclusions and future works. decentralized heat recovery ventilation units. Mono units, which are used as decentralized heat recovery ventilation devices due to their small scale compared to standard ventilation devices, are generally used in residential applications and meet the ventilation needs of one room or one office. And they are compact and easily mounted on a wall or a window and do not require air ducts. You can mount this device with using this channel on the wall or the window. Fans in here, there is a one fan or two fans, filters, and the heat exchanger in here are critical components of this device. Heat exchangers are the most important elements, as you know, that greatly affect the efficiency and energy saving of all ventilation systems together with mono units. Generally, metal plate heat exchanger are used in large volume ventilation systems, and ceramic hexagonal or honeycomb heat exchanger, regenerative heat exchanger are used in mono units. These type of heat exchanger are produced by traditional production methods and are easily available due to their monotonous structure. For this reason, hexagonal channel ceramic heat exchanger are used in all mono units available in the market. Actually, we will change the in here. We will change the heat exchanger with triply periodic minimal surface heat exchangers, and I will explain what is the minimal surfaces or triply periodic minimal surfaces. Actually, in here there is a historical timeline. Studies on minimal surfaces started with Euler's catanoid geometry in 1744, and the Meissner helicoid geometry followed him in 1776. Then, actually, these are the most commonly used geometries in the literature. In here, sorry about that. Yeah. Studies these are actually minimal surfaces, and the studies on triply periodic minimal surfaces started with the design of the geometry called as Schwarz primitive surface, and which is created at 1865. Then sorry about that. His student Neuwies developed the Schwarz diamond geometry, and after almost 100 years, Schoen created his own geometry as gyroid. Yeah. Actually, a soft film is one of the minimal surfaces, and we can encounter these minimal surfaces on the nature. You can see the insect and the butterfly wing, and you can encounter in the butterfly wing gyroid geometry, and the weevil insect you can encounter with diamond geometry. Also, you can see the Munich Olympic Stadium, and these it combined minimal surfaces. Okay, triply periodic minimal surfaces can be created by using these trigonometric functions. You can create them with using MATLAB or Mathematica program. TPMSs have two separate non-intersecting three-dimensional channels that provide a higher surface area and volume ratio. Two flows at different temperatures pass through the TPMS without mixing with each other, and the heat transfer can be easily. The mean curvature is 0 at any point on the TPMS, and since each channel is interconnected in all directions, so the flow can move freely in any direction. Thanks to the eddies formed in the TPMS, during the flow, the dirt and particles accumulated on the surface will be removed from the surface, and the heat transfer efficiency will be increased. TPMS exhibits natural structural integrity. Also, these structures, due to the heat curve structure, the pressure applied to the both sides of the TPMS will be equal. Thus, they can withstand tough working conditions such as high temperature and pressure. Due to the above mentioned properties, TPMS have a potential to be used as a heat exchanger. However, this kind of structures cannot be produced traditional methods, metal forming or turning, forging, or other something. So we need to use additive manufacturing methods. And what is additive manufacturing? Actually, additive manufacturing can be used in different kind of regions or different kind of regions. And you can see the economical advantage, society advantage, and environmental advantage. You can control the pollution and the other something, and there is, in general, there is no waste in the additive manufacturing method. Actually, we use the fused deposition method in our study because FDM is chosen because it's cheap and its filaments are easily available in the market. In conjunction with heat exchanger, outer body is also produced with the FDM 3D printer, so it's easy to produce something for us, and then we use this additive manufacturing method. As I mentioned, the third page, you can create these geometries with using MATLAB or mathematical geometry. And you can see the diamond, primitive, and gyroid geometries at different porosity values. Actually, before this study, we performed the CFD analysis. So in here, as you can see in here, honeycomb and primitive geometries have very low heat transfer coefficient. But diamond and gyroid geometries have very high heat transfer coefficient. So we prefer these geometries for our experimental tests. And we produced our geometries only at 0.6 porosity due to the time consumption. And as I mentioned, we only use diamond and gyroid geometries in here. Actually, as you can see, the gyroid geometry, and this is our channel in here. This channel, as you can see, as you can see our test system components in here. The experimental setup is designed to extract the data to obtain actual performance decentralized heat recovery ventilation system. And we use the gyroid and diamond geometries. The output of the experiments is included 5 temperature measurements: hot inlet, hot outlet, cold inlet, cold outlet, and ambient temperatures. In addition, pressure drop has been measured for both hot and cold sites with using 2 probes. As is, also, I will show you the schematic diagram of the experimental step for better understanding. And actually, in here, as the working principle of the mono units, warm stale air is extracted with the premise flows through the regenerator or regenerative exchanger and transfer its energy to the heat exchanger. As the ceramic heat exchanger gets warm up and units switch to supply mode, clean cold intake air flows through the generator and absorbs accumulated heat. When the ceramic or the other heat exchangers is cooled down, then the unit switch to extract air mode, and this application, which can be described as a combination of hot and cold flow, and we called as a cycle. Okay, then we have four temperature probes with 1 more and 5 ambient temperature probes, and we have two pressure sensor in here. As you can see, we have two flow meters, and we have PLC to read the temperature and the air flow rate values, and we have one heater and two fans. In here, our main parameters. Actually, we calculate the heat recovery efficiency with using this formula. Also, we choose the cycle time 60, 80, and 100 seconds. Because actually the commercial system cycle time it varies in 60 and 70 seconds. So we want to see the different kind of situations. We prefer the cycle time these values, and we had to change the hot and cold flow change time, and we assume that 10 seconds. Also, in here, we use the 100, 120, and 140 meter cube per an hour Birol flow rate, and as I mentioned before, our porosity 0.6 also. Actually, here 100 and 120 meter cube per seconds are corresponded to the airflow rates generally used in the commercial systems. In order to examine the performance of the system at the higher flow rates, tests also carried out at a flow rate 140. As I mentioned before, the cycle time in commercial system 70 seconds, and we prefer these values to see the effect of the cycle time. In here, as you can see, our experimental results. In the upper figures, the heat recovery efficiency values, the only diamond heat exchanger are shown in 4 cycle times for 60, 80, and 100 seconds respectively. According to obtained data, the efficiency increase as the cycle time and airflow rate is increased also. The efficiency, heat recovery efficiency increases as the cycle time and airflow rate. Also, the increasing cycle time efficiency values at different flow rates approach each other in here, as you can see. The highest efficiency value of approximately 66% is obtained for 140 meter cube per second airflow rate at the 100 second cycle time. In here, in the lower figures, the heat recovery efficiency values of the gyroid geometry are shown for the same cycle times. According to the obtained data, the efficiency increases as the cycle time and airflow rate increase, as similar with diamond heat exchanger. Also, with the increasing cycle time, the efficiency values at different flow rates approach each other as like the diamond. However, unlike the diamond geometry, the efficiency values exceed 90% at some points. In addition, also the cycle time thermal efficiency values or heat recovery efficiency values are very close to each other for all flow rates. Accordingly, it can be said that the flow rate does not have much effect on the gyrate heat exchanger. And with the high efficiency values obtained, the lower flow rates, the pressure drop will be reduced also. In this way, the required fan power will be reduced also, and the energy saving will be achieved. This shows that the gyrate heat exchanger is suitable for use in heat transfer applications for thermal efficiency or heat recovery efficiency. In here, general conclusions and future works, it's seen that the gyrate geometry reaches higher thermal efficiency values compared to diamond geometry, regardless of the cycle time, especially for the 100 second cycle time, the efficiency values are reached the level of 90% like commercial systems. Regardless of the cycle times, thermal efficiency values are very close to each other for all flow rates. Accordingly, it can be said that the flow rate does not have much effect on the gyrate heat exchanger. Also, with the high efficiency values obtained at the low or lower flow rates, the pressure drop will be reduced. In this way, the required fan power will be reduced, and the energy saving will be achieved, as I mentioned before. This shows that gyrate geometries can be used as heat exchangers in heat transfer applications. The future works. Honeycomb heat exchanger to be produced and compared with the gyrate and diamond heat exchangers also. And thank you so much for listening to me.
Much, Alper.
Can you hear you clearly, but
do you hear me now?
Yeah, I can hear you now. Okay.
Okay, I have a question.
Yes,
Actually, I understand that you manufactured your heat exchanger in a 3D printer, correct?
Yes, correct.
And you used filaments.
Yes, of course.
Fiber filaments. Can I ask you the conductivity value of the fiber filaments?
Yeah, actually, it's very, very low compared to metal heat exchangers. Actually, it's close to ceramic heat exchanger. But we are, how can I say, we want to see that the heat transfer capacity of this heat exchangers,
okay, so,
not the thermal conductivity.
You compared each case among each other. So, so there is a family of fiber,
yes, of course.
fiber stuff, fiber material. However, you try to understand which geometry is the best, is the best geometry.
Yes, of course.
For the maximum heat exchange or heat recovery factor.
Yes.
Okay, thank you very much.
Thank you so much.
And I assume this was your PhD, right?
Yes.
All right. Okay. Thank you very much, Alper, for this informative presentation.
Thank you.
This brings us to the end of session 5 and also to the end of our second day in the symposium. I hope we see each other tomorrow. We will start again at 1 o'clock and we will have one session right after 1 o'clock, and then this session will be followed by 2 panels. So I hope you had a very fruitful day with us, and I sincerely hope to see you, the attendance of the symposium tomorrow. See you, and bye-bye.